I have the honor to introduce to the Professor Dr. Johannes Edvardsson. He comes from the Department of Geology, Lund University, Sweden. About his biography, the Dr. Johannes Edvardsson is an associate professor at Lund University, specializing in dendrochronology and climate change impacts on ecosystems. With a PhD in geology and postdoctoral research at the Swedish Terrain Laboratory, he has led a groundbreaking project like Climate Pit, focusing on terrain analysis to understand long-term climate variability. His works on multimillennial terrain chronology from oak and pine in Scandinavia has provided critical analysis and insights about the science into the past climate transitions, making him a leading expert in paleoclimatology and climate modeling. The topic that he will speak in this conference is related with the following. So Scandinavian terrain records from subfossil trees as proxies for long-term climate variability and ecosystem change. So you can start there, Professor Johannes. And yes, we can see your presentation. Maybe if you put completely your screen, will be good.
So, can you hear me now?
Yes.
Okay, great.
We can hear you.
Yes.
Maybe,
Thanks,
Dr. Johannes, maybe could you put your screen complete? Because it's only in the PPT.
Okay, strange. I can see it as, let's see.
Yeah, okay.
Do you see it? The screen shared now?
Okay. No.
No, okay.
No.
Let's see.
You could try.
Better like this?
Yeah, in that moment, yes.
Yes, okay.
It's ready.
Then I continue like this. Yeah.
Okay.
It's yeah, sometimes weird with two screens at the same time. Yeah. Okay. So thanks for the introduction and thanks for organizing this nice meeting. And so I'm Johannes Edvardsson from Lund University, and I've been working with a lot of different types of dendrochronology. So with living trees to reconstruct cause and effects of tree colonization on peatlands, and also with archaeological and historical buildings. And for example, a bit similar to what Andreas was talking about, but one of the favorite topics is, of course, with about subfossil trees and very long reconstructions we can do using subfossil oak and pine trees. And since, let's see, should be possible to change. Okay, let's see if I try. Okay, now it changed. So since we have 30 minutes, quite a lot of time, it's possible for me to give some background information also about these studies, because it's a very long and time-consuming projects to build these long chronologies, and it has involved many people's, and the first samples that I will included in my chronologies were sampled and measured already in the 1970s. So it's a very long process. And if you talk about subfossil trees from Scandinavia, of course, you have to mention the Tornet-Kresk chronology. Andreas already mentioned it. And this is the longest continuous chronology we have in Scandinavia, so 7,400 years. And all the material is from a quite limited area in the Lake Torneträsk and the catchment area. But this is far up in the north Sweden, very close to the regions where Andreas is working, and this material doesn't correlate or cross-date with the material in South Scandinavia that I'm working with. So I have to build up something myself, and then I have to look for the material that I can find in peatlands. We don't have this kind of cold lakes like in northern Sweden and northern Finland preserving wood. Instead, we can find well-preserved old wood in peatlands. And this is nothing new in dendrochronology. Already in the 1970s, there were a lot of studies in Ireland and Northwest Germany, where they started to build up long chronologies during the 1970s and the 1980s. But then I start to look at what we could do in South Sweden. But I guess since the audience is quite mixed, I can take one slide just to describe a little bit what the peatland is and how it's developed and some of the ecosystem services that peatlands provide for us. So in Scandinavia, we have a quite young landscape. So 20,000 years ago, during the last glacial maximum, everything was covered by 2-3 kilometers thick ice sheet. But then during the deglaciation, the ice melted away. We have a undulating topography and a young landscape with a lot of lakes in Sweden, Finland, and in the Baltic countries, for example. And in all of these small lakes, they are gradually getting more shallow, at first from minerogenic material, but then when the climate is getting warmer and it's more vegetation in the catchment area of the lake and living organisms in the lake, there will be more and more organic material starting to build up a stratigraphic sequence in the lake, and it's getting gradually more and more shallow. So in the second picture from the top, we can see that the organic layer has reached the lake surface and the lake has become a wetland instead. And then it's possible for different kind of trees to start to establish. It can be alders in the beginning, that is very moist tolerant species. And then later on, when different moss layers start to develop and reaching above the water surface, also pine trees can start to establish. And then when the peat start to accumulate, different layers with tree trunks and tree stumps will be preserved in the peat. And in the lowermost picture, we have a raised bog developed, and peatlands and raised bogs, there's a very thick organic layers in them, and they are therefore important carbon sinks. So even if the peatlands in the boreal zone only covers about 3% of Earth's land surface, they store twice as much carbons actually as the forests. So they are very important in the global carbon cycle. However, today I will talk about the peatlands as climate archives, because we can also extract peat sequences to study variations in the peat, to look at warmer and drier and colder and wetter periods. And we can also use pollen and plant macrofossils preserved in the peat to reconstruct the climate. And of course, we can use the trees, both the living trees and the trees preserved in the peat, to develop tree ring chronologies and reconstruct the climate of the past. And this is something that has been done for quite a long time. So I mentioned the long Irish and German chronologies developed during the 1980s. And one important person developing many of the long chronologies in Northwest Germany is Hubert Leuschner, to the left. He was at Göttingen University, is now retired, but he developed several long pine and oak chronologies that has been important for the work that I will present. And we also have Kjell Christensen in the middle, and he's started to develop the long oak chronologies in Denmark that I continue to develop now recently. But I will focus then on the peatlands in South Scandinavia, and why is the peatlands great for this kind of development of long tree-ring chronologies? Well, it's the preservation conditions in the peat, since it's anaerobic conditions, so no oxygen. Organic material is very well preserved. So one famous example might be the Tollund man. He was found in a Danish peat bog in the 1950s. The people that found him contacted the police. They thought he was murdered. The police came. They couldn't identify him, and but they thought the clothes were strange. So they contacted archaeologists. He was later radiocarbon dated, and he's been dead for 2,500 years. So it was a cold case for the police, but it's a very good example on how good organic material is preserved in peatlands. And the same goes for wood then. So the pine trunk in the middle, it's included in my chronologies, and the outermost ring is 4,970 before the Common Era. So it's been dead for almost 7,000 years, but amazingly well preserved. And at peat extraction sites, we can find really a lot of this kind of material in certain layers of the peat extraction sites. Of course, this is a problem for the peat mining company. They have to remove all the trees, but it's very convenient for me. I can go there and sample a lot of trees. So this is some of the reasons why it's favorable conditions, both the conservation and that we sometimes can find a lot of material as well. So back in 2006, I started to work with some subfossil trees in peatlands in South Sweden. And in 2008, I started as a PhD student to develop these pine chronologies. And one of the breakthrough during my PhD work was when I started to compare my long pine chronologies with long pine chronologies from the Lower Saxony area developed by Leuschner. And what we found was that even if it was like 500 to 700 kilometers between our study sites, we could find significant cross-dating statistics during our long chronologies. So sometimes t-values between 7 and 11. So it was a convincing and very strong cross-correlation. And this didn't only prove that my chronologies were okay, it also proved that gave them an absolute age to calendar years, and it also proved that it must have been quite similar climatic condition in a quite large part of the Northwest Europe during the mid-Holocene. A bit later on, I also started to find oak trees in the peatlands, and then comparing my oak chronologies to Danish oak chronologies, and the Danish oak chronologies were then also dated using the Northwest German chronologies. So we seem to have a bit some teleconnections in here in Sweden, Denmark, Germany. So what I'm trying to do then was to see which chronologies were matching each other and what chronologies we might be able to use for some kind of paleoclimate reconstructions. But we still don't have the connection with the northern chronologies like the Tornatresk chronology and so on, for example. But the study region that I will focus on now in the rest of my presentation, when we start talking about the chronologies that I'm building up, it's oak material found where we have the red dots on the map, and the pine chronologies, it's the green dots. And as you can see, it's a lot of different study sites included, especially for the oak trees. So we have a very mixed material when we consider the oak trees. It's material from archaeological excavations, it's findings from peatlands, it's also when people have been digging drainage ditches, they might find oak trunks that we could use. And actually there is also like a black market, so to say, for this kind of old oak samples, because they are quite valuable. So people would want to build things of these black oak samples. And so I actually start contacting some people selling this kind of material just to ask them, can I date your material and use the data for my chronologies? Maybe it's more valuable when you will sell it if you know the age and so on. So I've been trying to find material everywhere to build the chronologies as long as possible. Then the pine material is much more homogeneous. So it's all from this kind of peat extraction sites. Some peat material has been removed by the peat mining companies, but some tree stumps I can still find at the position where the tree were actually growing thousands of years ago. So I then can take a GPS point and knowing exactly where the tree has been growing back in the past. So when we consider the oak material, what I ended up with when I start to merge the Swedish and the Danish material was like 40 different chronologies. And the blue samples, so the line shows how the trees are overlapping each other in time. So the blue samples are the oak trees that are absolutely dated to calendar year. And whereas the gray groups of samples in the lower part of the picture shows the radiocarbon dated chronology. So they are still like floating, but radiocarbon dated. But this material then cover most of the last 8,000 years. And if we take a look at the tree replication records from the oak material, we can see the blue periods are absolutely dated material. The gray curves show the radiocarbon dated material, and the pink periods show where we still have this kind of annoying gaps in the tree ring chronology that I'm trying to bridge now by finding new material all the time. And if we combine the oak and the pine material and focus on the Swedish-Danish material, we have a pretty good coverage of the last 8,000 years, but some gaps in the oak records in blue and some quite large gaps in the pine records, especially over the last 3,000 years. I have difficulties to find pine material actually. But what can we learn from this kind of material? It just looks like a mess when I find it in a peatland like this. Well, if we start to look at the tree rings, we can see quite strong reactions and changes in the tree growth. So the trees must have been sensitive to something. And if we move to peatland environments today, we can see that we have a groundwater table very close to the surface. So actually the root systems of the trees are more or less in level with the groundwater table. So these trees will be very sensitive to water table changes. So when we have a water level increase, the trees will almost drown. And so we have a kind of hydroclimatic signal in the trees. So I will start with one study using peatland pines. And so this is a peatland called Vismos in South Sweden. We can zoom in on a little bit on the peat on the study site. So the black border shows the peat mining area, and the black dots are in situ pine trees, so I know where the trees have been growing. And the open circles are trees removed from their growth position. And then we also have a coring point in the middle of the peat land where I have a peat stratigraphic core also. So from the pine trees, I was able to build a 726-year-long tree ring chronology. It's absolutely dated, and it starts 5,284 before the Common Era. So we're roughly 7,200 years back in time when the trees start to grow. So on the tree replication record in the middle, we can see some kind of tree establishment phases when we find more and more material, and then a sort of gradual decline of material around 6,700 years ago. And in the tree ring records in the lowermost graph, we can see the year-by-year growth variations of the trees, and interpreted as wet years in blue and drier periods in yellow. And if we try to put this material in a longer context, we can compare it with a peat record. So from the peat stratigraphy, I can follow a story from a lake that is gradually becoming a wetland and then a peatland. And we have measured the density variations in the peat, because during warmer and drier periods, there will be more oxygen involved in the peat degradation process and less moss growth also. So we will have a more dense peat during warm and dry periods. And exactly during the period with highest density in the peat, it's actually where we find the trees. So this indicates that the pine trees were establishing on this peat bog during a relatively warm and dry periods during the middle of the Holocene, actually the Holocene thermal maximum. So it was a warm and dry period. So this knowledge combined with knowledge about where different trees were growing make it possible to reconstruct the development of this peatland from a lake before 9,000 years ago into kind of a wetland 8,000 years ago, where we can find some pine trees establishing. The yellow circles are radiocarbon dated pine trees. 7,200 years ago, we can find a bit more of the absolutely dated pine trees, and then we can probably, it's getting drier and drier during this Holocene thermal maximum, so we can see spread of pine trees across this peatland around 7,000 years ago, and around 6,700 years ago, we can see more stressed trees, and probably it's getting a bit wetter again. So it's possible to do quite detailed reconstruction based on the pine trees. But as I mentioned, we also have oak trees. So if we combine the oak and pine trees, we can get an even more interesting story. So the black dots are the pine trees, and the gray dots are the oak trees. And if we start to look what kind of context we find the different tree species in, it differs. So the pine trees I can find in the middle of the peat sequence. So we have several meters of organic material below the stumps, and we have several meters of organic layers above the tree trunks also. So they are in the middle of the peat sequence. However, the oak trees are found in the marginal zone of the peatland. So it's a much more shallow organic layers. So you can actually see on this photo that there are rocks penetrating the thin peat layers. So the oak tree's been almost growing on minerogenic soils, whereas the pine tree's been growing on peat soils. So if we make a comparison to present day conditions, I would say that the pine trees were growing in a very moist conditions like this and sensitive to hydrological changes, whereas the oak trees were growing on slopes next to the peatland and probably a bit more temperature sensitive. But then after dying, the oak trees might fall out in the peatland and be preserved, or they might be killed when the peatland is expanding during wet periods, burying the small slopes and the oak trees. So we can then make a sort of a small reconstruction of the peatland based on both the pine and the oak trees, and we also have alders, the red dots. So if we take a look along this dashed line, it will look something like this. So 7,000 years ago, we have the peatland with the pine trees to the west of this small ridge, and we have some kind of wet opened landscape to the east of this ridge. 4,500 years ago, the peatland has grown on the height and buried the pine trees, so they are preserved in the middle of the peat now. And we have some kind of wetland area with alders to the east of this ridge. 1,000 years later, we have a mixed forest. So we have oak, I find alders, I find ash trees in this kind of a still wet environment to the east of this ridge. 3,200 years ago, I find oak samples on top of the ridge also, just for a very short window of time. So my interpretation is that this is the time when the peatland is expanding and growing over the ridge, killing and preserving the logs from these oak trees. So we can make a pretty detailed site reconstruction. So but how did the climate change over this period of time? Yeah, if we look at the tree replication records again and compare the oak in blue and the pine in green, we can see it looks very different, the pine and the oak trees. So it's a very different signal. So during the cold 8.2 event, I don't have any much material, but then I find quite a lot of oak. But then during this Holocene thermal maximum, when it was getting warmer and drier, then I find a lot of pine material. So during warm and dry conditions, the pine trees could establish and spread across the peatlands. According to the pollen records, there was oak trees around during this period of time, but I don't find them because probably the preservation conditions are pretty poor around the peatlands, so the peatlands are not expanding. However, towards the end of the Holocene thermal maximum, around 5,000 years ago, then I don't find any pine, but I find oak trees, and we have a wet shift we can see in the peat records over this period of time. So probably the peatlands start to expand again, preserving oak trees. And then we have this kind of a bit shaky period when I find both pine and oak trees. But during this cold 2.8 event, for example, I find a lot of oak trees, but no pine trees. And over the last 3,000 years, I have very little pine material. Probably it's a bit too wet conditions over this period of time. However, over the last 200 years, then it looks like we have an increase of pine trees again. So it might be related both to land use changes and to climate change. We can look more into detail as well and look at the tree ring data, of course, in the long chronologies. So this is one pine chronology to the left and an oak chronology to the right, and both of them are covering the main part of the Scandinavian Bronze Age. And of course, the there are several interesting events happening during this period of time. One of them might be the volcanic eruption in 1628 before the Common Era, sometimes attributed to Terra, but in this paper by Charlotte Pearson, it's attributed to the Aniakchak 2 volcano in Alaska. No matter which volcanic eruption that was responsible, it was a climate change that we can see in tree rings all over the Northern Hemisphere. So we have narrow rings in the following years in North America, in northern Finland, in Siberia. So what happened in South Scandinavia over the following years? Well, if we zoom in on the tree ring records and start with the oak trees. So the volcanic eruption was 1628 before the Common Era, and 1627 and the following 4 years in the oak record are very narrow rings. So below -1 standard deviation from the average. So it seems to be immediate response in the oak trees, but a more gradual response in the pine trees. So they are growing almost normal in the year after the volcanic eruption, but then gradually growing less and less over a 7-year-long period. So probably if it's getting colder, we have less of evaporation from the peatland. So it's gradually getting wetter and wetter, and it's getting tougher and tougher for the pine trees over a 7-year period after this volcanic eruption. So it seems that we have different types of climate signal in the pine and the oak trees that is interesting to combine them. And if we continue to look at this pine chronology over the Bronze Age and start zooming in on different trees, we can look at a period starting around 1400 before the Common Era to 1170 before the Common Era. We can see a lot of changes actually. So at first we have a tree colonization period around 1400 before the Common Era. So in yellow, interpreted as relatively warm and dry conditions, so the trees are establishing on the peatland. Then starting in 1289 before the Common Era, we have a 19-year-long growth depression phase. It looks like this in the tree rings. So it's probably getting pretty cold and wet for a period of time. The trees are suffering, but surviving. And then we see strong growth again. But then around 1200 before the Common Era, we see very narrow rings again. The tree survives, but then during the 1170s before the Common Era, it seems to be too wet or extreme conditions. All the pine trees dies within just a couple of years. So really dramatic change. And actually, so this is around 1170 before the Common Era. And this is basically the same period of time as the oak trees I was talking about before are buried by this expanding peatland. So it all connects. So it seems to be a change towards wetter and colder conditions in South Scandinavia during this period of time. However, around the Mediterranean, it seems to, that is kind of books the year when the civilization collapsed, but there are also like tree ring based studies showing that we have a drought around the Mediterranean during this period of time. So there seems to be this kind of changing patterns similar to what we can see in the jet stream or the North Atlantic oscillation patterns that we could actually trace them by if we can combine the information from the Scandinavian subfossil trees and Mediterranean material. And this is something that will be the next step in the studies we are doing with this material. So take home message, well, you can learn a lot about climate and environmental history by using subfossil trees, but it takes forever to build this kind of chronologies we've been working since the 80s with these chronologies, and it's still a lot of work to do. But that was it. So thanks a lot for your attention, and feel free to ask me questions. Thank you.
Thank you so much, dear Dr. Johannes Edvardsson. Nice presentation and very interesting. We know about the challenge that face when you are working about this type of research is very, very interesting and hard too. So we have a question from the Dr. Andreas. Dr. Andreas, feel you free for make your question that you write in the chat here. Please, could you turn on your microphone? You're welcome.
Yeah, that was not a question by me, but I just reacted to somebody asking about clearings in the tropics or near tropics.
Okay.
But maybe I can ask Johannes. I just work in the southern Norwegian mountains with some fishing traps, and I got interested in these dry phases.
Okay,
That has something to do with preservation of those coasts. I just wonder, would you expect some similarities between southern Sweden and the tree ring chronologies in mid-Sweden, the Jämtland chronologies in the mountains?
Yes, I think that's of course something to look more closely into details, but I think there is similarities between what we can when we find a bit drier phases in the south and the central Sweden, and the studies that Björn Gunnarsson has done, for example, in Jämtland. He combined, he made this long pine chronology from material similar to the Torneträsk material, so from lakes, but they also have peatland, short peatland tree ring chronologies that fits into these kind of phases when the trees could colonize and then during a dry phase and then be buried and preserved again. So I think it's should be a similar pattern. I think and it would be interesting to find if you to compare maybe these fishing traps, what water level depth they are built in, if it was the same, but of course, but they are marine environment, or is it lake environments in the fishing traps?
That's like,
okay, yeah.
And today it's a tree line site, 800 meters above sea level.
Thank you so much.
Thank you.
Maybe other participants have any question, please feel free for making this. Yeah, okay, very nice. And so we will, any participants want to make you a question? Maybe I call her. Okay. So, dear Professor Johannes, I have a little question. When you are making your sampling with a fossil tree, subfossil tree, how you collect this sample? With increment border too?
No, so since these samples often are quite fragile, and it's no like they they are not protected or so. So I can use the chainsaw to take discs from the samples. It's the easiest and quickest way, and then it makes it possible for me to measure in several directions also, since sometimes they very slow growing and missing rings and things like that. So I go for taking the discs with a chainsaw for these trees.
I see the last time that when you are making your measurements about this terrain, you use other type of equipment for this, right?
Yes, I guess you think about the tests I've done with CT scanning, for example.
Yes.
Yes, so that's something we are testing, and it promising, but it's a bit time consuming, and also it costs to take these images and to use the CT scanners. But I think it could be good for if you would like to make wood anatomical studies on the early wood in this oak trees. That's my idea, to test with CT scanned images. But usually when I just measure the ring width, I go for the stereo microscope and the measuring table, and the classic way to do the tree ring measurements.
Oh, very interesting and very nice and new techniques, especially when we are working in South America. Okay, normally we don't have this opportunity to work with this equipment, but I think it will be very, very interesting in the future. Try to prove or test with this type of equipment. Very interesting there, Professor. Thank you so much for the question.
Yeah. Hello.
Yeah, okay, see, you are welcome.
Yeah, it's me, Fayaz Asad from Pakistan. Sorry, I joined it a little bit late, but I have very simple questions from Professor. So, dear Professor, I have collected the juniper trees around 3,900 meter elevations from in north part of the Pakistan, and we are able to develop the millennium scale chronology. During the field visits, there is a lot of significant number of deadwood trees in the surface of that mountains. So we could consider that as a sample, as a subfossil. What samples are? No, we just looking at behind the rocks samples.
So what was the question? I heard about the juniper trees that
I'm repeated
you...
that. Okay, I'm repeated. I have collected the samples from juniper trees. It's living trees, right? And we are able to develop the millennium scale chronology.
Yeah.
In that surface, there is a lot of dead trees, right? But we are not sure that will be the age of that dead trees. We are ignore it in that time. So we could consider that wood sample is a subfossils.
Yeah, I would go for the dead trees also if they are well preserved, so you can see and measure the rings. Then you can go for it, and hopefully maybe extending the chronology even further. And if they don't match, a first step could be of maybe to radiocarbon date this material also, to see how old it is, if it's worth to continue to work with, and extend the chronology even further back. But up in very dry mountain regions, dead wood can be preserved for a very long time. So sometimes you can find 1,000-year-old tree trunks that are very well preserved. So it would be interesting to continue with that material, I would think. Yeah.
Thank you, Professor.
Yeah.
Okay, thank you so much, Dr. Johannes.